Hi students, and welcome to Preliminary Chemistry and the Chemical Earth video series. In this one I want to have a quick look at really just introducing the idea of three-dimensional structures and contrasting ionic and covalent substances with those of metallic elements. So just a brief intro then. The structure of any substance is really a reference to how the particles within the substance are arranged. Now we can have discrete molecules, we can have atoms, we can have ions, it doesn't matter, but we're really looking at how they are arranged in space in three dimensions. One of the important things that we'll look at later is that the arrangements or the structure of different substances actually affects not only their properties, but also their ultimate purposes. So in chemistry, we have this sort of flow from understanding the structure to what are the properties that are going to be evident in that substance based on that structure, and then to what uses can we put that particular substance based on those properties. For this video, we're just going to have a quick look through each of the four major categories in order to get an understanding of how this kind of works. So the first one we want to look at are covalent molecular substances. So these are covalent compounds that form discrete molecules. And these discrete molecules are arranged can be arranged certainly in solid form with a number of different types of what we call intermolecular or between molecule forces holding those molecules together. So if you think of something like ice, ice is just solid water. Now for the water to be solid, those discrete water molecules, which will look something like this, have to actually be held close together. As water vapor, or what we often refer to as steam, each individual water molecule is quite separate and discrete from each other. But in a covalent molecular solid, each of these comes very close together and forms actually a linked structure by not only the bonds within each of the molecules, but bonds between molecules. So that each of the oxygens, for example, would then be held not only to the two hydrogens that it is covalently bonded to, but through these intermolecular forces from one molecule to another. To give you a little bit of an idea about how this works, you can see that here in this particular example, we may have something like hydrogen, H2, two hydrogen atoms, or O2 or N2, you can pick whatever you want. And between each of these, there is a very strong covalent bond. But if we were able to cool this down, so if it was hydrogen, for example, hydrogen has a very, very low boiling and melting point. But if we were to cool it enough that it would form a solid, then we would find these two discrete molecules actually coming closer and closer together until there was a very weak force of attraction between the two molecules. Now we're going to have a look at exactly what the nature of those intermolecular forces are in future videos, but for today, just understand that with these sorts of discrete covalent molecular substances, there are different types of attractions between the molecules that are much weaker than those within. Nevertheless, they are strong enough to hold them in a solid kind of configuration. Contrast that with something like a covalent network. What you see here is something like carbon in the form of diamond. Now this is a three-dimensional network where each individual carbon atom is bonded to four other carbon atoms in an entire network array kind of a situation. There's no discrete molecules here. Each one of these carbon atoms is connected in the network structure to four other carbons, and this is one of the things that accounts for particularly something like diamond having an extremely high hardness. There's just no weaknesses within this particular solid, and that's a characteristic of these sorts of covalent networks. Silicon dioxide is equivalent to the quartz in beach sand, and whilst it's not as hard as diamond, diamond sits on top with a hardness of 10 on the Mohs scale. Quartz is 7, so it's still very, very high, a very, very hard substance, as a result of the network bonding between the silicon and the oxygen. So these sorts of covalent networks can exist for both elements as well as compounds. Now we also have ionic compounds, and ionic compounds also form arrays in the same sort of way as the covalent networks, but now instead of being a single atom or a compound of a couple of atoms that are bonded to each other, these are discrete ions. So each is an individual ion, a cation or an anion, and they may have formed in one way by the donation or acceptance of an electron, but now they're being held in bonds in all different directions. And you can kind of see that by tracking a single individual positive charged cation and see how many negative anions are surrounding it. So this is another type of network structure that we find very commonly in ionic compounds. Of course, this is a very simplified one, so this would be a ratio of 1 to 1 for cation to anion, something like sodium chloride. For something like sodium oxide, where you have 2 sodiums for each oxygen, the structure looks slightly different, but we will look at crystal structures later. And the final one I just want to quickly mention, just to get your minds thinking about that, is what metals look like. And the thing with metals is we know that metals are very good conductors, and that means that there must be some flow of charge, and that flow of charge is the electrons. Electrons are these little green dots here, and metals have only 1 or 2, generally speaking, 1 or 2 valence electrons, outer shell electrons. They're fairly loosely held, and they're equally sort of attracted to other nuclei of adjacent atoms, and so therefore these electrons can actually drift around this structure. When you apply a potential difference between the two ends of the metal, then you get them all flowing in the same direction, and hence you get conductivity. This sort of arrangement is often described as islands. The cations, the positive ions, are little islands in a sea of electrons. So all of these electrons just sort of moving randomly around these metallic ions. But we'll look at metals in a little more detail in a future video. So thanks for watching.